Okay, let's take a look at this problem. Air is contained in the variable load piston cylinder device. That means that the pressure can change, variable load. Initially, the air is at pressure and temperature. The paddle wheel, which is that little guy down at the bottom, little propeller, spins, and that's adding energy to the air. And they tell us how much energy is being transferred. There's also Q. They show it going in. I'm not sure if it's going in or out, but anyway, I'll show you how to deal with whether or not it goes in or out. So they're going to maintain a constant air temperature, but while they do that, the volume of the gas triples from what it is now. And what they want me to do is find out what the Q is per kilogram. Right? Okay, so I'm going to pause it. You think about it. How would you approach this particular problem? Okay, all I've done here is write down some of the things that we know about this. It's an ideal gas. Notice that I'm going to use the standard units, and so I'm going to use everything in newtons, meters, seconds. So kilopascal, I want pascals, and so the pressure is 400,000. Also, because this is an ideal gas, I'm going to use absolute temperatures. So the T1 is 17, and you add 273 to get Kelvin. The work from the paddle is equal to 75,000. That's going in to the gas. The Q is unknown. It's drawn as entering, but the question we have right now is it really entering? The T2 equals T1. The volume 2 is 3 times the initial volume. And then also for specific volume, the volume per mass, that's also going to be 3 times the input. Okay, so think about these conditions and what you plan to do to solve the problem. So give it some thought, and I'll pause. Okay, here what I've done is I've written the energy equation for the air that's in there. So on the left-hand side, I'm going to take all of the energies that are going in and out. So I have the paddle wheel work, 75,000. The reason I'm using 75,000 is because those are kilojoules, and I want to use standard units. So that would be 75,000 joules. Those would be a Newton times a meter, which are the standard units. I'm writing this per kilogram, and so I'm writing it as little q. The total amount that goes in would be little q times the mass that's in there. So depending on what you want to do, I'm writing it per kilogram. All right, so that's little q. The arrow shows it going in, so I put it in as positive. Now, when I solve for q, if I get a positive number, that's correct. It's going in like I thought. If I get a negative number for q, then what that means is you're adding a negative energy. Negative energy would be something that's coming out. That's how you would know whether it's going in or out. Okay, so there's the Q. And then I have expansion, because if it's getting a larger volume, then it's expanding. Expansion work has got a negative number. That's why it's negative there. And I don't know how much right now, so I'm just going to write it as W expand. But I put a negative on there because I'm assuming that well, I know it is. It's going to be coming out. Okay, and that equals the change in energy inside the air. That would be, it has no kinetic, no potential, that sort of thing. So it does have, the only thing it has is internal energy. So in the red equation down here, just below it, this comes out of chapter 5, where the U of an ideal gas is equal to this heat capacity times the temperature, okay? Because it is the same temperature, the U final and the U initial are the same, so the right-hand side is equal to 0. Okay, give some thought to what you're going to do about it. By the way, I've circled the things that are unknown. I don't know Q, and I don't know W expand. So I've got 2 unknowns, and I only have 1 equation. So rather than trying to solve for anything right now, I'm just going to keep going. So give it some thought as to what would be the next thing to do, and then I'll pause it. Okay, the next thing that I'm going to do is try to find out what is the expansion work. And because I know it's an ideal gas, I write down the ideal gas law per kilogram. So pressure times the specific volume, the little v, is equal to the gas constant for air, which is known, we'll look it up in the table, times the temperature. Well, the gas constant and the temperature are constant, so that means that P times V is equal to a constant. Now, if you remember, constant P times V to a power equal constant is a polytropic process. So that is P times V to the N is equal to a constant. So this is polytropic with N equal 1. I'm going to show you some notes out of chapter 5 for finding the work. Okay, here's a section from the lecture notes in chapter 5 where it talks about what a polytropic process is and shows you a little diagram over here on the PV diagram. And it tells you what the work equation is. So this is the work equation for a general polytropic process. It also shows you what the work is if n is equal to 1, which is the case that we have right now. A work is always, when you plot the process on a PV diagram, it's always the area under the PV diagram. And how do you find that? Well, a number of ways you can. One is by using calculus 2 and doing what they call an integral. But anyway, they've done that for us, and so I'm just going to use this formula. Okay, so we're back to the problem. Here in blue was the ideal gas. That's what told me that it was polytropic and the N was equal to 1. And then from the previous slide from the notes, they gave me the formula for the work. So it's in blue, P1V1, natural log of the volume ratios. It's also, if you want to, you can use the red one. There's, because it doesn't matter what P and V that you use. The blue equation, if you plug into that, it will be exactly the same as the red equation. This one over here ought to be the V2. Left that off there. Okay, so I'm going to plug into these guys. So now what you have is, if you circle the unknowns, you don't know Q, you don't know W expand, and if you use the red equation, you don't know V2. So there's 3 unknowns and 2 equations that are listed there. Okay, so think about what you're going to do next, because you need another equation. You're missing one. Okay, so you think about it, and I'll pause it. Okay, so here's the rest of it in black. You see that this is basically just the ideal gas equation, P times little v equals RT. From that equation, you're able to solve for the little v1, which I did. It's 0.208. Make sure that you can get that number as well. Once you have v1, you can then get v2. It was given in the problem. It was 3 times v1, so v2 comes out in a trivial way. You need the R and the C for air. You'll find that in table A2. So that's where those numbers come from. And then with the 2 volumes, you can plug into the red equation or the blue. Makes no difference. You'll get exactly the same number. And you calculate the expansion work, which is 91437. Taking the expansion work, then you can go back up here to the top equation and calculate the Q. The Q ends up being 16,437. Now, what are the units? Because the answer is 16.4. Why do I get 16,000? Because I'm using standard units, and the standard unit is joules, not kilojoules. So if you want kilojoules, you just divide this green number by 1,000. Okay, that's it.